Welcome to this presentation from the P1 unit on specific heat capacity. Specific heat capacity is about how much energy it takes to heat different objects made of different materials. So we're going to look at how much energy it takes to make a cup of coffee. So when you turn the kettle on, the heat energy goes to 3 different places. Take a couple of seconds now to work out where it goes, and then I'll tell you. Okay, firstly, it goes into the water inside the kettle. Well, that's where we want it to go, but not all of the electrical energy that's supplied to the kettle goes there. Some of it goes into the plastic, the actual body of the kettle, and some of it is transferred through the body of the kettle out and heats the air around it. So, the big question is, how do we know how much of the energy that we've supplied via electricity is actually being turned into heat energy in the water, and how much is being wasted? Now, there's a number of equations that we need in order to be able to do this, and we're going to look at these on the next slide. The first equation tells you the power rating of the heater. Now, whatever you're using to heat, whether it's a kettle, whether it's an electric heater, a hairdryer, they will all have a power rating. And underneath you should be able to find a label with the electrical output, and it will give you the voltage and the current. And if you multiply the voltage and the current together, that gives you the power, and the unit of power is watts. You will need to be able to rearrange this equation in order to make voltage and current the subject. The second equation actually tells you how much energy is being transferred via electrical energy from the heater into the kettle itself. So the amount of energy, like all energy, is being measured in joules, and that is power times time. So you'll need the power bit from that equation and the time that the kettle is turned on for in order to calculate the amount of energy. So that's the energy being supplied by the kettle, but not all of it is going to go into the water itself, as we saw on the previous slide. In order to calculate the amount of energy that goes into the water, you need to know 3 things. You need to know the specific heat capacity of the water, the mass of the water in kilograms, and the change in temperature. Now, the specific heat capacity tells you how much energy is needed to heat 1 kilogram of water by 1 degree. So that amount of energy, which you're going to see in a minute, you'll obviously need to multiply by the number of kilograms and the temperature rise. You are going to want to refer back to this slide at various points during the presentation, as it's got all 3 calculations. Now we're going to look at all of these 3 in turn and how they link together. So this is a table of the specific heat capacities of different materials. As you can see, different materials require different amounts of energy in order to heat them up. The one that we're interested in for this equation is water here. However, any of these different ones here could be asked for. It's important to look on the question to find out the value of the specific heat capacity, as sometimes they round it up to make it easier. You might see the water value as 4,200. Make sure you use the value on the exam paper, not one that you've remembered from this revision session or from your exercise book. So here's a question about a kettle. A kettle with a voltage of 250 volts and a current of 12 amps. And there are a number of questions. Firstly, what's the power of the kettle? Secondly, how many joules of electrical energy were expended, i.e. how many were supplied? Thirdly, how much energy it would actually take to boil 1 kilogram of water if you started at 20 degrees, and how much energy was wasted, i.e. the difference between the amount of energy supplied in electricity and the amount of energy that was actually used by the water to boil it. You're now going to try and calculate the power. You're going to need to refer back to that previous slide, the one where it gives you the different calculations that you need. So I'm going to give you a few seconds now to pause this and work out the power of the kettle. Now you've had a chance to work it out, I'm going to go through the equation with you. Let's see if you got it right. Okay, so the first thing that you need to do is you need to write down the equation. And the equation is this here: power is voltage times current. So all you need to do is you need to look up those values. So the voltage is 250 volts, the current is 12 amps, and you multiply them together. 250 times 12 gives you 3,000 watts. Now that's fine, but you could also convert that into kilowatts, and to do that you need to divide it by 1,000. So watts into kilowatts, you divide by 1,000. It is really important that you make sure that this K here is lowercase, it's not a capital K. However, the W is a capital. Right, the second equation requires you to work out how many joules of electrical energy were expended to boil the kettle. The kettle took 2.5 minutes to do it. So if you refer back to the previous slide and find the equation, and then in a few seconds we'll go through the actual answer. So you're going to want to pause this slide, do the calculation, and then look at the answer. Now you've had a chance to calculate the amount of electrical energy expended, let's have a look at the answer. Okay, so now you've had a chance to do the calculation, let's have a look at the answer. You use this equation here, energy is power times time. Well, you calculated power in the first part, which is 3,000 watts, and then time is 150. Now some of you, I'm sure, will be scratching your head going, well, why is time 150? Because it took 2.5 minutes to boil. Well, what you need to do is you need to convert minutes into seconds. Okay, so obviously 1 minute equals 60 seconds. So you've got 2 minutes there, which is 120, plus half a minute, which is 30 seconds. So that gives you the 150 seconds that you need there. You multiply those two together and it gives you 450,000 joules. Just like before, you can convert the joules into kilojoules just like you did watts into kilowatts by dividing it by 1,000. And again, you need to make sure it's a lowercase k, not an uppercase. So far, you've calculated the power of the kettle and the amount of electrical energy that's been supplied to boil the water. Now we need to look at how much energy has actually gone into the water to raise it from 20 degrees to boiling point. It's time to refer back to that slide again to find the equation for the amount of energy required to heat water. So go back to that equation, write it out, and then try and do the calculation. Don't forget you're going to need to know the mass of the water and this starting point, and don't forget we're trying to find how much energy it takes to boil the water, so you need to think about how you're going to need that 20 degrees in order to work out the amount of energy. Right, now you've unpaused it, you've had a chance to do that calculation, let's have a look at the Right, so the first thing is to write down the equation. The energy transferred to the water is the specific heat capacity of the water multiplied by the mass of the water multiplied by the rising temperature. So you go back to that table and you've got the specific heat capacity of water is 4,181 joules per kilogram. We know that we had 1 kilogram of water, it says so in the question, that's there, and the rise in temperature. Now we started at 20 degrees and obviously everyone should know that the boiling point of water is 100, so 100 minus 20 gives you this 80. And you end up with, you multiply them all together and you get 334,480 joules. Just because it's not a whole number of joules and kilojoules, you can still turn it into kilojoules by dividing it by 1,000, and that gives you 334.48 kilojoules. Now, if this was an exam question, you can either use joules or kilojoules in your answer, unless it actually tells you at the bottom of the answer section whether it wants it in joules or kilojoules itself. If it doesn't give you joules or kilojoules, there will be a mark available for it, so make sure you put it in. So now the final equation is to look at how much energy was wasted, because we know the amount of electrical energy that's been supplied, and we also know how much energy it took to heat the water. And you should see already that there's a difference between the two, and we need to find out where that went. You now need to try and work out the difference between those two values. If you pause this slide and do that calculation, we'll look in a couple of minutes about the actual value that you should get and find out where that extra energy's gone. Now you've had a chance to do that, go on to the next slide and we'll look at the answer. Right, so the energy amount wasted is the energy produced by the kettle minus the energy transferred to the water. So the energy that we produced that went in by electrical energy is this value here, 450,000 joules. And from that we know that 334,480 went into the water itself. So the difference between those is 115,520. And again, you can convert this into kilojoules. Well, if we go right back to the third slide, we talked about where the energy went. It could go into the plastic kettle, and of course this is a solid, so it can go by conduction, and it can go into the air by convection. We will be covering conduction and convection in greater detail on a future slide. Right, now we're coming to the end of this revision session. You should now be able to do the following things. You should be able to calculate the energy produced by a kettle or any other electrical device, because it's all exactly the same. It doesn't matter whether it's a kettle, a hairdryer, a toaster, an oven. The calculation is exactly the same. The same with the amount of energy required to heat water. As long as you've got the specific heat capacity of the water, you can work it out. And again, it goes for other substances. So if you get a question where it's not about heating water, you need to look on the question for the specific heat capacity value of that other substance. The other thing to be wary of, if it is a question about water, is you use the value that they provide, and it may be 4,200 rather than 4,181 that we've used in this. And finally, you should be able to give reasons for the difference in the energy supplied and the energy output. So where did that extra energy go? So still to come in this series, there's going to be revision sessions on specific latent heat and conduction and convection. So look out for those in the near future.